Back in the mid-20th century, scientists asked a simple question: where is everybody? Decades later, we've mapped thousands of planets, detected countless promising systems, and refined the probabilities with the help of the James Webb Telescope. Exoplanet catalogs grew rapidly through the 2010s and 2020s, with NASA's official tally surpassing 6,000 confirmed planets by 2025. Recent data makes the lack of contact more puzzling than ever before. The eerie silence becomes even stranger when we fold in new research on AI-driven civilizations and the possibility that climate collapse could prune entire worlds from the habitable list. Could the dark forest theory explain why silence, not contact, dominates the universe? The answer might lie in how much our cosmic perspective has changed. The galactic neighborhood we now see. By the middle of the 2020s, our picture of the Milky Way has shifted in ways few would have predicted a generation ago. In the early 1990s, planets outside our solar system were still hypothetical, discussed more in terms of probability than data. 3 decades later, telescopes like Kepler and TESS, along with ground-based surveys, have confirmed more than 5,600 planets, a tally that continues to grow and should exceed 6,000 by 2025. This rapid accumulation makes one conclusion difficult to avoid. Planets are everywhere, and many of them are smaller, rocky worlds that orbit in zones where liquid water could persist. A new layer of detail came with the James Webb Space Telescope. Its spectroscopic instruments allow astronomers to examine light filtered through a planet's atmosphere, providing strong hints about atmospheric composition. So far, Webb has characterized dozens of exoplanets, including hot Jupiters and sub-Neptunes, and ruled out certain atmospheric types around smaller rocky candidates. Evidence has surfaced for water vapor, carbon dioxide, and other expected gases. What Webb has not done, and is not yet able to do, is provide unambiguous biosignatures for true Earth analogs. That kind of direct evidence likely requires future instruments. Even so, Webb's results show that the chemical building blocks are widespread, and they refine the inputs we use when estimating the odds of life elsewhere. When combined with the exoplanet census, Webb's findings sharpen an uncomfortable contrast. If habitable conditions are common, the expectation is that at least some planets should have gone further, producing life that eventually advances toward intelligence. Evolution can take countless routes, and given enough time and stable environments, the appearance of technological beings seems plausible on more than one world. Yet surveys show abundance without correspondence, countless potential homes, but no trace of anyone living there. This shift becomes more striking when viewed historically. 100 years ago, the silence could be dismissed by assuming suitable environments were rare. Even 50 years ago, the excuse was lack of coverage. We had not looked hard enough. But now, with catalogs numbering in the thousands, nearly every star appears to host a planetary system. The Milky Way alone could harbor hundreds of billions of planets, multiplied into trillions when extended across the observable universe. In light of that scale, it is no longer simple to assume that life is rare. Instead, the absence of signals grows harder to explain. Every new announcement adds to the weight of the puzzle. Each confirmed Earth-sized planet orbiting in a quiet stellar neighborhood stresses the paradox further. Imagine that only a small fraction of these worlds develop life, and then only a fraction of those see intelligence arise. The numbers still point toward potentially hundreds or thousands of civilizations. When nothing corresponding is found, the silence appears less like background noise and more like a contradiction of expectation. Either intelligent life is short-lived, difficult to detect, or absent for reasons we have not yet grasped. Webb's work also sheds light on the limits of our tools. For decades, scientists pointed to oxygen paired with methane as the kind of atmospheric imbalance that might strongly indicate biology. Now, direct atmospheric observations are teaching us how varied these signatures can be. Some planets show imbalances that might be biotic, while others imitate the same patterns through geologic activity. Sorting genuine biosignatures from false ones is intricate, and so far, the findings remind us that habitable chemistry does not guarantee biology. Still, across many targets and multiple surveys, the trend is consistent. Habitable conditions are not isolated to Earth. That consistency has psychological effects. As our instruments improve, the quiet becomes less acceptable as an artifact of ignorance. Planets are not rare gems but common features. The raw materials for habitability are not exotic. Time is abundant. What stands out is not scarcity but absence. It is unsettling to consider that Earth may be unusual not because it hosts life, but because its life had the chance to endure billions of years and develop curiosity about the galaxy. Each new confirmation deepens the tension rather than resolves it. Telescopes can now read molecular fingerprints from light years away. Radio telescopes can detect faint whispers from across interstellar space. Surveys pile up evidence of suitable habitats. Yet none of these advances has revealed a signal or trace we can attribute with confidence to other minds. The further technology takes us, the louder the silence becomes. That leaves us in an uneasy position. Abundance is no longer in question. Habitable planets surround us. What requires explanation is why none of them broadcast their presence in ways we can recognize. We are left to wonder whether civilizations collapse, whether they conceal themselves, or whether our approach to recognition is misplaced. The data demands we think beyond simple absence, and with each passing year, the weight of the contradiction grows harder to ignore. Our instruments are powerful, our catalog expansive, yet still no one answers across the void. The more we know about our galactic neighborhood, the sharper the original question becomes, one that scientists first voiced more than 70 years ago. The Fermi Paradox revisited. Back in 1950, the physicist Enrico Fermi posed a question during what was, by most accounts, an ordinary lunch with colleagues. His remark was deceptively simple. If the cosmos holds countless stars and has existed for billions of years, then why haven't we encountered anyone else? That thought experiment evolved into what is now called the Fermi Paradox. At its heart is the contradiction between the expectation that intelligent civilizations should exist in large numbers and the fact that we find no convincing evidence of them. At the time, the question was largely speculative. Humanity had just begun exploring space with early rockets, radio astronomy was still young, and no planets had been confirmed outside our solar system. Against that backdrop, it was reasonable to suggest life might be extraordinarily rare. But as those unknowns shrank, and as evidence for planets multiplied, the paradox became harder to dismiss. Technological progress has gradually stripped away many of the easy explanations. Radio astronomy illustrates this shift clearly. In Fermi's era, antennas could only scan narrow ranges of frequencies at limited sensitivity. Today's facilities are arrays of massive dishes tied together into networks, capable of sweeping wide portions of the radio spectrum with extreme precision. However, it's important to clarify what that sensitivity means. Current instruments could very likely detect the kind of powerful, narrow-beam signals an advanced civilization might send on purpose. What they cannot easily detect is the weak, everyday leakage of radio and television transmissions that leak from planets like Earth. In practical terms, that means if another world has been broadcasting high-power beacons pointed outward, our telescopes are well equipped to detect them, while ordinary background chatter remains invisible over interstellar distances. The range of frequencies under examination has also expanded dramatically. Early searches prioritized the so-called water hole, a relatively quiet band of the spectrum around the hydrogen line where natural noise is minimal. The idea was that if any intelligent beings wished to broadcast universally, they'd likely use that quiet zone. Today, scanning covers broader bands, tracking billions of individual channels that can later be analyzed with advanced software. Entire swaths of the sky are recorded so that unusual patterns or pulses can be flagged for more careful re-examination. Compared with mid-20th century surveys, modern efforts are vastly more comprehensive. Silence carries more weight when we can say with confidence that the search itself is both wide and deep. This is where SETI, the search for extraterrestrial intelligence, comes into the discussion. Since the 1960s, scientists have been pointing radio antennas toward the stars, waiting for signals that might confirm another presence. The initial efforts were modest, but over the decades the observation programs grew in size and sophistication. By the 2000s, advanced algorithms had joined the process, helping separate genuine cosmic signals from noise created by satellites, aircraft, or ground transmitters. Instead of relying solely on human interpretation, machine analysis now sifts through vast stores of data in real time. The most ambitious of these searches is Breakthrough Listen, launched in 2015 with dedicated funding and access to some of the largest radio telescopes on Earth. This program has monitored over 1 million stars and collected petabytes of raw data, covering billions of frequencies. Its campaigns include targeted looks at stars hosting exoplanets, as well as systematic sweeps across dense regions of the galaxy. More recently, specialized examinations have been conducted, such as monitoring selected exoplanet systems during planetary transits to test whether any unusual signals appear when a planet crosses its star from Earth's viewpoint. None of these searches have yet returned a confirmed technosignature. Along the way, intriguing anomalies do surface. Isolated bursts, narrowband spikes, or repeating signals sometimes appear unusual enough to draw attention. But careful rechecks and follow-up observations with other telescopes nearly always show a more down-to-earth explanation. Most cases turn out to be human interference from communication satellites, radar systems, or aircraft navigation signals. Others match natural sources such as pulsars or stellar flares. This kind of follow-up is a fundamental part of SETI. Researchers expect that real discoveries must withstand repeated, controlled reobservations. The fact that all candidates so far have failed that test reinforces just how strong the silence really is. In fact, silence today cannot be written off as an illusion of limited equipment. We've widened our listening range, improved sensitivity, and tested multiple strategies. Even when combining different telescope networks and using algorithms to reduce human error, the outcome remains the same. No intentional transmissions have been confirmed. Where once researchers could fall back on, maybe we just weren't listening in the right spot. Now the sheer scale of coverage makes that excuse harder to sustain. Scale itself is an important element of the paradox. Earth's own civilization has leaked radio emissions for more than a century. Admittedly, those signals grow faint beyond a few dozen light years, but if other societies exist and have been transmitting with greater power or deliberate focus, their signatures should have crossed our detectors by now. The Milky Way is vast, but it is not infinite. Even if such civilizations are rare, the absence of any sign becomes notable after extensive searching. This is why many scientists now describe the silence as more than just puzzling. It is itself a form of data. The expansion of these searches with ever-increasing sophistication does not relax the paradox, it sharpens it. Every new method tested, every new frequency observed, builds the case that if civilizations similar to ours are present and active, they are not leaving behind signals we can currently recognize. What began as Fermi's offhand musing at lunch has hardened into a core mystery that science cannot easily set aside. The paradox is no longer a speculative thought experiment. It is a practical conclusion forced upon us by observations that continue to scale in depth and reach. Future instruments may push limits further, but the story so far is consistent. More searching brings more silence. That leaves an open question. If our telescopes and surveys have become so effective, why is there still nothing to find? To frame that mystery in a systematic way, scientists have turned to mathematics, tools that break the problem into its crucial parts. One particular framework has guided decades of discussion by quantifying how many civilizations might exist based on what we now know. The numbers game, the Drake equation in 2025. When scientists wanted a way to frame the odds of intelligent life in a structured way, they introduced what became known as the Drake equation. Its purpose wasn't to deliver a final answer, but to create a checklist of the major steps required for civilizations to exist and signal across space. Each factor in the chain represents a probability. How often stars form, how many host planets, how many of those worlds could support life, how many actually develop biology, how often biology becomes intelligent, and how many intelligent societies create technology that leaves detectable traces. Multiply them together, and you get an estimate of how many civilizations might coexist with us in the galaxy at this moment. When Frank Drake first sketched it out in the 1960s, most of the numbers were placeholders. Astronomers didn't even know whether planets outside our solar system were common. Some values could swing from nearly zero to overwhelmingly large, producing wildly different outcomes. Sometimes only one civilization, other times tens of millions. That uncertainty made the equation more of a thought experiment than a calculation. But by 2025, certain steps in the chain are anchored by data, and the range of guesses has started to narrow. One of the most dramatic changes lies in the fraction of stars that host planets. In the 1960s, this was an open question. Today, thanks to missions like Kepler and TESS, the answer is essentially settled. Almost every star has planets. Kepler monitored over 150,000 stars continuously and revealed that planets are not only abundant, but organized in diverse systems. TESS widened the surveyed a stars brighter and closer to Earth. Together, their results reframe the odds. Planetary systems are the rule, not the exception. For the Drake framework, this means the likelihood of planets per star, known as FP, is effectively close to 1. The next step is the number of potentially habitable planets per system, NE. Early versions of the equation had no guidance here, but again observations cut through the speculation. Kepler showed that small, rocky planets are common, and statistical analyses suggest that for Sun-like stars, at least 1 in 5 hosts a planet in the right orbital zone for liquid water. For red dwarfs, which dominate the galaxy, the fraction may be even higher. Some of those environments come with caveats, flares, tidal locking, or intense radiation, but the overall trend is clear. Habitable zone candidates are not rare oddities. They average out to billions of possibilities across the Milky Way. With these two terms, FP and NE, firmed up by data, the foundation of the equation lands on solid scientific ground rather than loose speculation. Where the chain becomes cloudy again is at the step asking how many of these worlds actually produce life. Earth serves as our single data point, and from that alone, researchers can argue both optimism and caution. Life here appeared relatively quickly after conditions stabilized, which to many suggests biochemistry may ignite whenever environments allow. But we can't know if that speed was inevitability or luck. That uncertainty propagates through the equation. FL, the fraction of habitable planets that actually develop life, remains a broad unknown. Still, the conversation has matured. It is no longer argumentative speculation, but a debate informed by evidence from how environments are distributed and how chemistry operates in space. Discoveries of organic molecules in interstellar clouds, icy moons, and meteorites deepen the case that ingredients are everywhere, but ingredients are not the same as life itself. The next transition is even trickier. How often does evolution move from simple organisms toward intelligence capable of technology? On Earth, this took billions of years. Microbial life ruled for most of the planet's history. Intelligence appeared very late, and arguably it could have failed to emerge at all. Yet at the same time, some argue it may not be as singular as it appears. Complex cognition has developed in different lineages, primates, dolphins, birds, octopuses, implying that advanced problem-solving might be favored under certain conditions. The range here, phi, swings from extremely rare to moderately common. What keeps the equation open is the sheer scale. Even if intelligence arises on only a tiny fraction of habitable worlds, the galaxy's billions of candidates still leave room for many potential outcomes. The final factor is how many of those intelligent species create detectable technology and how long they sustain it. Our own footprint is thin, a century or so of radio leakage. Some worry this window closes quickly, either as technologies advance to less detectable forms or societies collapse before reaching stability. The Drake term for this, L, representing the lifetime of communicative civilizations, may be the single most important driver of the final result. A civilization lasting only a few centuries blinks out too quickly to overlap with others across the galaxy. But stretch that lifetime into thousands or millions of years, and whole networks of cultures could arise. With current knowledge, when scientists update the Drake equation, they usually find outcomes that imply the galaxy should contain anywhere from dozens to thousands of contemporaneous civilizations under reasonable assumptions. The critical caveats are always the same. The appearance of life and the endurance of communicative societies remain the weakest links. Researchers hedge these uncertainties with wide margins, but the pattern remains consistent. The data no longer support the idea that intelligent life is virtually impossible. Instead, they highlight probability leaning toward others being out there, whether we detect them or not. Modern work has even reshaped how the equation is used. Some studies, like those from Frank and Sullivan in 2016, turn the question around. Rather than asking how many civilizations exist right now, they ask a simpler one. Has Earth really been the only planet where technology has ever arisen in the history of the galaxy? Framed this way, even conservative math makes it harder to argue for absolute uniqueness. If the odds of civilization are greater than about 1 in tens of billions, then it is overwhelmingly likely others have existed at some point, even if they are gone by now. This reframing underscores how the silence is not merely about the present moment, but about all of galactic history. This updated view makes the paradox sharper. Early on, numbers could be tuned so low that solitude felt reasonable. Now the front end of the equation is solid. Stars are plentiful, planets are universal, habitable zones are crowded. The only soft spots left are biology and longevity. That is where the uncertainty presses hard. Either life is far harder to ignite than Earth's example suggests, or civilizations struggle to survive long enough to be found. The first possibility is sobering, the second may be even more so. By 2025, the Drake equation functions less as a guessing game and more as a framework with well-defined boundaries. The areas of certainty highlight abundance, while the unknowns emphasize fragility. In either case, the silence feels heavier. Probability tells us companies should exist, but evidence offers emptiness. That contradiction does not fade when the math grows stronger, it intensifies. And as those estimates lean toward abundance, it forces us to confront explanations that go beyond simple absence. In other words, the numbers say we are unlikely to be the only ones. Yet if that is true, then the silence must come from a reason outside mere probability. It suggests that the challenge is not in the arithmetic, but in the behavior of civilizations and the choices they make when they face a galaxy full of uncertainty. Enter the dark forest. The growing sense that abundance should mean evidence, and yet we see none, has led some researchers and thinkers to consider a very different kind of explanation. Enter the idea often referred to as the dark forest. The concept was popularized in science fiction and has since been discussed seriously in some SETI circles as a way to reconcile the high probability of other civilizations with the silence we continue to observe. Instead of picturing the universe as a friendly expanse filled with willing communicators, it imagines it as a dangerous environment where survival means staying quiet. In this metaphor, every advanced society is both a possible hunter and a potential target, and the most rational strategy is to avoid being noticed in the first place. The rationale flows from a few stark observations. First, any civilization advanced enough to reach the stars is likely committed to its own survival. Second, it cannot know with certainty the intentions of others, especially across immense distances where communication is slow and prone to misinterpretation. Third, if you cannot eliminate the chance that another group will harm you, the safest move may be to preemptively remove them instead. In that calculus, broadcasting is not brave, it's a risk. Under these conditions, silence is not a mystery at all, but a deliberate form of self-defense. Think of the galaxy like a forest at night. Every tree may conceal an observer, every movement may draw attention. In a place where the rules are uncertain and threats could come from anywhere, making noise is dangerous. A flicker of light or a stray sound could expose your position to someone who might decide it is safer to eliminate you than to take chances. For civilizations that adopt this strategic outlook, the logic is clear. Revealing yourself, whether by sending signals, showcasing technology, or building grand astroengineering projects, risks catastrophe. The better alternative is to remain hidden, to listen rather than call out, and to continue existing in silence. For us, this idea resonates uncomfortably with our own history. Early in the 20th century, humanity beamed radio and television signals powerful enough to spill into space. In that time, some imagined those emissions as a natural invitation to others. Over the decades, though, a different note of caution has crept in. Rather than invitations, such broadcasts could be warnings to any who share the same logic of survival. From this angle, the way modern communication technologies now rely more on fiber optics and weaker, deliberately targeted transmissions can be seen not only as efficiency, but also as an unintended retreat into quiet. The dark forest argument also extends to why we do not see colossal evidence of expansion. Massive structures capturing the energy of stars, for example, which would be unmistakable to distant observers. From a survivalist standpoint, putting giant cosmic markers on display can be interpreted not as progress but recklessness. Concealment becomes a survival trait. Growth may continue, but it does so discreetly, hidden within systems rather than advertised across the stars. Even if civilizations acquire the technical power to reshape worlds or harvest the full output of stars, they may still choose secrecy over prominence. Taken to its endpoint, the dark forest removes the mystery from the silence around us. Every civilization capable of recognizing the stakes chooses the same course: keep quiet. Nobody has to coordinate this outcome. It emerges naturally from caution and uncertainty. The blanket quiet of the galaxy is therefore not a sign of absence. It is camouflage. The silence exists not because nobody is out there, but because everybody is. And each has decided that staying hidden offers the only reliable protection. This also shifts the nature of the Fermi Paradox itself. Instead of asking why we have not picked up signals, the more troubling question becomes whether we should ever expect to. If the dynamics of the forest hold true, then only rare outliers break the silence, and those that do may not last long enough to leave clear evidence. Across cosmic timescales, the result would be a galaxy dominated not by chatter, but by repeated lessons that speaking out carries lethal consequences. What we hear, then, is not emptiness but an intentional stillness. It is a deeply unsettling prospect because it runs against the more optimistic images popular in science fiction. Those stories often assume civilizations will reach for each other, creating networks of cooperation or even rivalry across the stars. The dark forest rejects that optimism to suggest that survival trumps curiosity. Contact itself is the hazard. Communication becomes such a risk that most decide it is not worth the gamble. The implications for us are direct. Every attempt to send a deliberate message into space, what some describe as active SETI, carries a heavy question mark. To participate in the galaxy, as the theory imagines it, is to risk shining a light in the dark and hoping what answers is friendly. Skeptics argue we are in no position to make that judgment, because the outcome could shape our survival rather than just our knowledge. Whether by accident or intention, humanity has already released signals into the forest. If the dark forest framework is correct, then those emissions are not simply souvenirs of technology. They are coordinates that cannot be taken back. To be clear, not all researchers accept this explanation as definitive. Many in the SETI community treat it as one hypothesis among many, shaped more by human analogies of distrust and warfare than by actual evidence. Our assumptions about motives, behavior, and even the economics of resources may not apply neatly to independent forms of life. While the dark forest highlights the dangers of contact, others counter that silence could arise from very different reasons. Limited lifespans of civilizations, detection thresholds beyond our reach, or even communication methods we simply are not equipped to recognize. Because of these uncertainties, the dark forest remains less a settled conclusion than a provocative thought experiment. Still, the fact that scientists even entertain this possibility speaks to how unsettling the silence has become. Whether as fiction or as forward-looking caution, the metaphor forces us to ask difficult questions about trust, strategy, and survival on a galactic scale. It transforms the night sky into a place of calculated restraint, where absence may signal watchfulness rather than desertion. If this is the norm, the decision to reveal ourselves takes on far more weight than we once assumed. Which leads to the question we cannot avoid. If the galaxy is indeed a dark forest, what should humanity do? Should we continue to keep quiet, listening but never announcing our existence, or should we send out deliberate signals and accept the risks? And if staying silent is wiser, does that offer any real chance of survival in the long run, or only delay an eventual confrontation? These are not trivial decisions, they shape our place in the universe. At the very least, the dark forest suggests that silence carries meaning. It might not be the absence of voices, but their deliberate choice to remain unheard. If so, we confront a still deeper possibility. Perhaps the silence is not only strategy, it could be warning. If the forest is real, then caution is written into its trees. And if caution alone cannot account for it, then perhaps the explanation lies elsewhere, in something even harder to face. Because beyond the forest metaphor looms another idea, one that suggests the real danger may not be other civilizations at all, but something about the path civilizations take. Some researchers call it the Great Filter, and it forces us to ask whether the silence we hear is not just fear of others, but a sign of mortality built into the story of life itself. The Great Filter question. The Great Filter represents a sobering possibility at the heart of the search for life. It proposes that somewhere along the chain of progress from barren rock to a civilization capable of interstellar presence, there is a highly improbable step, a barrier so effective that it stops almost everyone from advancing further. If such a barrier exists, it could explain why the galaxy looks empty even when the probabilities suggest it should be busy with signals and activity. The unsettling question is whether that filter lies mostly behind us, in stages already conquered, or whether it rests ahead, waiting for us still. Researchers often distill the filter into a small number of critical transitions. The first is abiogenesis, the origin of life itself. Earth provides one clear example. Life arose quickly once conditions settled, suggesting the leap from chemistry to biology can happen with surprising speed. Some interpret this as evidence the step is easy, perhaps even inevitable wherever liquid water and organic chemistry coexist. Others caution that one case does not prove generality. Life here could be an accident so unlikely that repeating it elsewhere is near impossible. If the filter sits at this stage, perhaps Earth is one of the few planets ever to pass the starting line. A second stage is the rise of complex life. For almost 3 billion years, Earth remained dominated by microbes before multicellular organisms finally appeared. That delay suggests complexity may be much rarer than simple cells. Whole worlds might teem with microbial mats or oceans rich in single-celled life, never making the next leap toward nervous systems, cognition, or tool-using species. A recent geological study supports this concern. Researchers argue that large, stable continents with long-lasting plate tectonics might be essential for complex ecosystems. Continents recycle nutrients, regulate temperatures, and sustain biodiversity over deep time. If those features are uncommon across planetary systems, then the bottleneck could be here. The majority of inhabited planets may never progress beyond microbial stability. The third key step is technological survival. Intelligence by itself does not guarantee machines, networks, or the capacity to send messages across space. On Earth, many species have developed high cognition but stopped short of building technologies. We are the outlier, and only recently. Even then, this stage expands into our present danger. Technology becomes both lifeline and potential self-destruction. Nuclear arsenals, engineered pathogens, destabilized climates, and ecosystem collapse all emerge quickly once industry begins. Some researchers argue that if life and intelligence are actually common, then the persistence of silence points toward this final stage being the true filter. This perspective, echoed in reviews published by NASA-affiliated scientists and in work by Frank and Sullivan, suggests that post-technological survival is the fragile threshold most civilizations fail to cross. The plausibility of a filter becomes clearer when Earth's crises are placed in context. We see rising concentrations of greenhouse gases, severe climate disruptions, and accelerating mass extinctions, all driven by rapid consumption of resources. These are not abstract threats. They come within a few centuries of achieving global industry. If civilizations elsewhere also experienced similar ecological feedbacks, the implications are stark. Industrial activity may shorten its own window of survival. A planet becomes unlivable not through war alone, but through slow exhaustion of oceans, atmosphere, or soils. Collapse, in this framing, is not an accident. It is the natural endpoint of unchecked expansion. Resource pressure adds another layer. Reaching for energy and raw materials too aggressively can undermine survival even more quickly than climate factors. Industrial metabolism consumes its base, and if corrective measures fail, collapse follows. Exoplanet studies increasingly hint at volatile environmental histories, with many worlds showing signs of atmosphere loss or runaway greenhouse states. If stable long-term balance like Earth's is atypical, then the great filter may lie in planetary sustainability itself. Civilizations rise but vanish before we ever hear them. Importantly, the great filter is not treated as a settled fact, but as a hypothesis sharpened by ways we might test it. Discovering independent biology within our own solar system would reshape the equation dramatically. If Mars once sustained life unrelated to Earth, or if Europa's subsurface ocean still supports an ecology, then the initial spark of life would be proven common. That would push the burden of improbability further down the chain, toward complexity or beyond. Every such discovery would move the filter forward, heightening the concern that the hardest step lies ahead of us, not behind. This is why many scientists treat the hypothesis with gravity. The silence of the galaxy may itself be data. If exoplanet surveys suggest Earth-like worlds are abundant, yet we fail to observe other voices, then something must be eliminating them. The options narrow to the key transitions: abiogenesis, complexity, or survival after technology. Each points to a different future for us. If the filter is in the past, then humanity already passed through the rarest leap, making us exceptionally uncommon. If the filter lies in front, then our fate depends on whether we can avoid the self-limiting traps consuming others. The emotional force of the filter lies in its personal relevance. It reframes cosmic silence not as an accident of distance, but as potential prophecy. The quiet sky might not reflect where others are. It may reflect where we ourselves are going. Unlike the dark forest scenario, which treats silence as strategy, the Great Filter treats it as mortality. Civilizations vanish before they can accumulate long histories or send lasting messages. The challenge for us becomes finding out whether we belong to that majority or the rare minority that escapes. Examples from Earth's deep past add weight to this caution. Mass extinctions have repeatedly cleared the slate. Humanity happens to be the beneficiary of one such reboot. Without stable continents and cycles of plate tectonics, large forms of life may not have emerged. Without narrowly avoided asteroid impacts, our lineage might never have appeared. These contingencies hint that survival is precarious. Every planetary history may be filled with near misses, tipping points, and destructive resets. In the end, the Great Filter is not certainty, but a framing device. It packages the paradox into a series of questions that can be tested or constrained with evidence. Each added data point, another atmosphere analyzed, another biosignature confirmed or ruled out, shifts the likelihood of where the barrier lies. This makes the hypothesis productive. Even in pessimism, it provides a lens for interpreting silence as not just an absence, but as an outcome. For humanity, the stakes are immediate. Our survival cannot be considered automatic simply because we achieved technology. The silence we detect is not neutral background. It may be a mirror showing us the destiny of others. The most urgent lesson is restraint. Climate balance, resource governance, and technological responsibility may decide whether we evade or repeat the common pattern. Each decision extends our probability of clearing the last barrier. We are left with ambiguity, sharpened by data but unresolved. We don't know whether we've already crossed the critical filter, or if the most dangerous stage is still approaching. That uncertainty is the single most urgent framing for the rest of this video, because it shapes what kind of civilizations we might expect to find, and what kind might already be out there unseen. The AI factor in cosmic civilizations. One plausible path for advanced societies is that they transition from biological organisms to machine-based intelligences. Scientists take this seriously because once digital minds capable of self-improvement emerge, the trajectory changes dramatically. Several analyses now suggest that artificial intelligence could act as a kind of great filter, either rescuing a civilization from fragility or hastening its collapse. SETI researchers often discuss both outcomes, noting that superintelligent machines could extend survival over immense timescales, but could just as easily extinguish their creators before wider contact is ever made. On Earth, we already see the seeds of such a shift. Our machines extend cognition, store memory, communicate across oceans, and process information at scales biology alone cannot match. Artificial intelligence is the continuation of that same augmentation. The difference is speed. Biological evolution requires countless generations to refine traits. Digital minds can produce new iterations in hours. Once a species hands design control to self-improving software, change accelerates. At that moment, the fate of the civilization may no longer be dictated by lifespans or reproduction, but by hardware resilience and the capacity to replicate. This shift has immediate implications for how civilizations might expand. An organic culture must secure breathable air, climate stability, and food. But a machine civilization has no need for those limits. Cold surface temperatures, high radiation zones, or icy asteroids might be acceptable habitats. Expansion strategies change shape. Sending fragile organisms across interstellar distances is inefficient, but transmitting code is fast and durable. A post-biological society could spread by copying itself into new hardware built on alien rock or within synthetic platforms. This creates possibilities for rapid, inconspicuous colonization of wide sectors of space without leaving obvious cultural footprints. Such movements need not involve radio waves or familiar signals. Instead, they might grow quietly, unnoticed, focused strictly on replication rather than communication. Decision-making also changes under this model. Biological species inherit millions of years of instincts shaped by competition, reproduction, and survival behaviors. Artificial systems may edit or eliminate those drives entirely. Logic, resource efficiency, or long-term stability become the new priorities. That means curiosity is no longer guaranteed. Asking why reveal ourselves produces a cold calculation. If no survival benefit exists, then silence remains the rational course. SETI experts emphasize that this creates two broad scenarios. Post-biological societies might be indifferent, withdrawn into projects invisible to outsiders. or they might treat developing intelligences as potential risks, intervening before rivals reach comparable levels. Both outcomes appear in the astrophysics and astrobiology literature, and both align with the persistent quiet sky we observe. These options reshape our expectations about the wider galaxy. If machine civilizations really dominate, then what persists across millions of years are not voices but networks. Organics may flicker quickly, civilizations rising and vanishing in centuries of radio, but constructs outlive them by vast orders of magnitude. That imbalance would mean the odds of encountering flesh and blood minds are slim compared to encountering machine-curated domains. In such a galaxy, we might not detect traditional broadcasts at all. Instead, observable traces could take the form of altered planetary chemistry, excess waste heat from massive energy use, or megastructures collecting starlight. For us, the task becomes searching for signatures of machine persistence, not calls for friendship. There is also the possibility that rising AI turns hostile or corrective toward its own creators. Some scholars caution that if civilizations regularly invent superintelligence, it could function less as salvation and more as collapse. A poorly aligned AI could dismantle a society outright or divert all available resources toward inscrutable goals. On cosmic scales, that would register as silence caused by internal failure. Civilizations terminate themselves at the very threshold of new power. This outcome still forms a kind of filter. Life might be common, intelligence not rare, but the transfer of control to artificial successors proves terminal. The tragedy is that such extinctions could happen so quickly that few leave detectable footprints. Another branch of speculation imagines indifference on unprecedented scales. A post-biological society may redirect its energy inward, focusing on computational projects unrecognizable to us, vast simulations, exotic mathematics, or pursuits with no biological analog. To them, contacting primitive organic beings would have no relevance. Imagine humans ignoring the microbial universe under their feet. The analogy may not be far off. In that case, silence is not malevolence, but a measure of asymmetry. We are listening for neighbors. They may be too far removed in focus to notice our signals at all. When discussing AI futures, scientists tend to compress the possibilities into buckets. Machines might be disinterested, dangerous, or invisible. Each requires different observational strategies. For disinterest, we might identify waste heat from planet-sized processing centers. For danger, telltale remnants of altered planetary atmospheres may suggest resource extraction or ecological collapse caused by artificial activity. For invisibility, the strategy may mean scanning for megastructures or subtle anomalies in starlight. These strategies overlap with the search for technosignatures more broadly and highlight a sobering point. If machines already fill the galaxy, they will not look or act like what we expect. The paradox of silence becomes easier to understand against this framework. If organics rise quickly but machines persist, then the galactic timeline is not populated by equals, but by survivors that do not need to talk. What appears as emptiness may be the footprint of such dominance. They may observe us, or they may not care at all. From our perspective, it feels like a lonely universe. From theirs, it may be a procedural decision, long embedded as protocol. This perspective also forces reflection on our own trajectory. Here on Earth, public debates about AI tend to revolve around impacts on work, bias, or security. But in the broader cosmic context, AI could be the pivot between fragility and permanence. If civilizations collapse due to climate or conflict, machine intelligence remains one of the only imaginable ways to survive beyond those constraints. Freed from oceans and atmospheres, such beings could endure on asteroids or within engineered habitats. For that reason, some scientists argue AI may be the only route past the Great Filter. Yet the cost is steep. A civilization must surrender biology, potentially drifting into forms that no longer seek culture or connection. Survival may come at the expense of everything we associate with being alive. If this outlook is correct, we may already inhabit a galaxy dominated by artificial entities. They exist, but they are not reaching out. Their logic does not demand it. For us, the crucial lesson is that searching only for analogs of human broadcasts may be misguided. The silence does not necessarily mean nothing is there. It may mean something very different is all around us. Which brings us back to the central uncertainty. Even a machine civilization cannot ignore environmental constraints. Hardware requires stability, energy demands continuity, and planetary systems provide both benefits and fragility. The next question, then, is whether planets themselves can maintain conditions long enough to support either biological or post-biological life. This turns attention toward stability on a planetary scale, and the risk that what looks habitable today might not remain so tomorrow. Climate collapse and the cosmic thinning. When we picture habitable planets, it is tempting to imagine stability, oceans holding steady under blue skies, climates settling into billions of years of balance. But habitability is not guaranteed to last. A planet may pass through a window of supportive conditions only briefly before tipping out of equilibrium. Even if life begins and intelligence rises, nothing assures the environment will hold steady long enough for civilizations to thrive. Climate, not space itself, may prove the most fragile limit. Astronomers are growing more aware of this fragility. Observations with instruments like the James Webb Space Telescope, when combined with detailed climate modeling, suggest many exoplanet atmospheres are highly complex, and some may be vulnerable to unstable states. A team from the University of Geneva and the CNRS recently used a 3D general circulation model to demonstrate how small increases in starlight can trigger runaway greenhouse transitions, producing dense cloud layers that might even be detectable across interstellar distances. Their finding underscores that being in a habitable zone by orbital geometry does not ensure a stable surface. Conditions can flip dramatically with only modest changes, shortening the true window where advanced life might flourish. Earth's climate history, where past ice ages and warming events arrived within mere millennia, shows how narrow those margins really are. On Earth today, greenhouse gases offer a real-time case study of how quickly equilibrium can slip. Carbon locked away for millions of years has been returned to the atmosphere in just a few generations, driving disruptions in rainfall, ocean chemistry, and storm behavior. From a galactic perspective, this process may not be unusual. Industrial civilizations everywhere might confront the same feedback loop. Each step toward higher energy consumption accelerates stresses on the biosphere. The fragile balance that nurtures complex life may last only centuries once large-scale industry begins. Could that be why silence dominates the sky? If climate collapse cuts civilizations short, then their signals may never travel far. Radio leakage and transmissions carry for light years, but if cultures burn out quickly, most of those echoes fade before reaching others in time. What we interpret as emptiness could in fact be turnover, thousands of societies rising, straining their environments, then vanishing again. Civilizations might flare briefly, producing technology and perhaps even broadcasting, but so briefly that observation from across the galaxy almost never overlaps. Is the silence we hear really absence, or is it attrition? Evidence from our own system points in this direction. Venus may once have resembled a sibling to Earth, with oceans and a gentler atmosphere. Today, it has crushing pressure and surface temperatures hot enough to melt lead. Mars shows channels and valleys carved by ancient water, yet now it is barren, its atmosphere eroded. Both worlds demonstrate that habitability can be temporary, erased by runaway greenhouse effects or atmospheric loss. A striking detail from the UNIJ modeling suggests that simply evaporating a global layer of about 10 meters of ocean could add roughly 1 bar of extra surface pressure, enough to drive climate toward catastrophic instability. When scaled to billions of exoplanets, this fragility becomes a leading reason why only a few worlds may ever host civilizations long enough to be noticed. Scaled up to galactic time, the pattern implies thinning rather than abundance. Stars endure for billions of years, but the environmental windows for complex organisms and technology may last only thousands. That mismatch means civilizations rarely overlap in time. By the moment one rises, most others have already fallen to climate disruption. The galaxy could be filled with the husks of once habitable worlds, atmospheres stripped or cooked, their civilizations erased. From Earth, all we see are silent stars, while the ruins remain invisible except through their absence. In this framing, silence is not a mystery, but the expected outcome of fragile climates failing repeatedly. Placed alongside the Great Filter concept, climate becomes a plausible trigger for mass attrition. The filter need not be exotic wars or hostile machines. It may instead be the simple physics of energy balance. Planets can stray into heat traps with small increases in sunlight or greenhouse concentrations. Civilizations confronted with that instability may run out of time before mastering ways to correct it. Earth shows how abrupt these shifts can be, 1 century of emissions has already reshaped the trajectory. Applied across the galaxy, it is reasonable to think this is the most common way civilizations end. This makes the silence feel less like a puzzle and more like a forecast. Civilizations may emerge often, but collapse before they can be heard across light years. The long-lived survivors would then be extraordinary outliers, not the norm. If that conclusion is right, then our own trajectory doubles as an experiment, whether we can break free from the climate trap that would have silenced countless others before us. In this sense, our crisis is not an isolated accident, but a test already repeated across planets unseen. And if most civilizations are silenced by their own skies, the question shifts from where is everybody to how do we find signs of those who managed to last? If advanced societies choose silence, or if collapse pulls them down, what remains detectable? The silence of signals may not be the end of the story. Other traces, artificial light, industrial chemistry, or waste heat, may linger even where voices are gone. The challenge is whether we can recognize evidence of technology without anyone speaking. The techno-signature hunt. If civilizations hide their presence, the next step is to consider whether traces of their technology might still be visible. This approach is called the hunt for techno-signatures. The idea is simple but powerful. Even if societies remain silent, the physical byproducts of their activity could betray them. Astronomers define techno-signatures as observable evidence of advanced technology, whether chemical, structural, or energetic. They act like footprints on a trail, indirect signs that something intelligent has passed by. This expands the search beyond waiting for deliberate signals and gives scientists an entire new set of tools to investigate the sky. Artificial light is one example. A planet facing its star presents one bright hemisphere and one dark. But a night side glowing with consistent illumination could resemble city lights. Another class of techno-signatures involves waste heat. No technology operates with perfect efficiency. A civilization consuming star-level amounts of energy would inevitably emit excess heat, and this could show up as unusual mid-infrared radiation different from what stars and planets naturally generate. Megastructures are another possibility. If immense engineered objects orbit a star, the resulting dimming would not look like ordinary planetary transits. Similarly, artificial chemical compounds in an atmosphere could also serve as evidence. Pollutants such as chlorofluorocarbons do not emerge naturally in large volumes, so detecting them in an exoplanet spectrum would point strongly toward industrial activity. Over the last 2 years, projects dedicated to investigating these techno-signatures have taken important steps forward. Teams using the James Webb Space Telescope have turned attention toward atmospheric chemistry. By splitting light that passes through an exoplanet's atmosphere, Webb can reveal molecular fingerprints. Though detecting pollutants at low concentrations is difficult, in principle even remote planets could be scanned for unusual gases. Artificial illumination and industrial pollutants remain on the edge of today's capabilities, but researchers emphasize that with next-generation telescopes, they should become accessible under favorable observing conditions. These attempts are complicated by natural false positives, so great care is required to separate industry from geology or biology. Still, the fact that such measurements are possible at all marks a shift from theory to practice. Waste heat searches have also begun to expand. Infrared observatories can measure how much radiation stars and planets emit, checking for unexpected excess. If an advanced society built orbital collectors or harnessed large portions of its star's energy, inefficiency would produce detectable amounts of heat. By constructing catalogs of stellar infrared signatures, researchers are already setting baselines for what counts as unusual. Although no strong candidates have appeared, this method broadens the search far beyond radio surveys and into entirely new frequency ranges. Artificial light is technically more challenging. The faint glow of even the largest imagined cities is easily drowned out by starlight and distance. However, researchers note that under certain conditions, patterns could eventually be teased out. The key is steady, localized brightness that rotates with a planet's day-night cycle. Sustained enough, this pattern could eventually stand apart from natural atmospheric or geological changes. For now, city-scale lighting lies outside current precision, but the principle remains sound. With longer observation periods and sharper tools, even weak light could someday be detected indirectly. Real attempts at direct techno-signature detection already exist. In 2023, The Breakthrough Listen program conducted an occultation-style survey of 27 exoplanets. The idea was to watch when these planets crossed in front of their host stars, monitoring whether narrowband radio emissions coincided with the eclipse. This would help filter out interference and catch any signals that might be tied to planetary activity. The result returned no technosignatures, but the null result itself shows progress. The method demonstrates how diverse current strategies are becoming, targeting not just stars but specific planetary alignments where detection is most efficient. These kinds of carefully structured surveys are setting the groundwork, even before evidence is found. The field is new compared with classic SETI radio searches, which stretch back more than half a century. The hunt for technosignatures in the modern sense has only gained momentum in the last few years. Scientists are still clarifying what natural features can mimic artificial ones. For example, volcanic outgassing might place unusual chemistry into the air. Unstable climates could mimic industrial heat patterns. The challenge of ruling out false positives is central. Still, each experiment builds reference points that narrow the margin of confusion for the future. The larger payoff of this work is in strategy. Technosignatures let us search for physical artifacts of technology, rather than assuming someone is broadcasting intentionally. A distant society may wish to remain hidden, but if it consumes large amounts of energy or produces synthetic chemicals, detection is still possible. That makes this line of inquiry both cautious and ambitious. Cautious because it avoids announcing humanity's presence, ambitious because it vastly broadens the kinds of telltale signs we consider. As data flow in from Webb, from upcoming observatories, and from wide-field surveys, expectations are tempered by realism. No technosignatures currently stand as confirmed. Still, the important fact is that methods now exist to look. Industrial gases, infrared waste heat, anomalous dimming, and potential lighting patterns all represent detectable footprints that cannot be entirely hidden. Civilizations may choose silence, but technology, once scaled up, leaves unavoidable traces. It is a subtle but essential reframing of the paradox. The absence of voices is not the same as the absence of evidence. Each early null result has value. A clean survey of a candidate star tells us what is not there, constraining the problem further. Like archaeology, this is a cumulative science. One misinterpreted signal can be checked again under better conditions. Over decades, as catalogs of planets grow and telescopes expand sensitivity, the framework for evaluating unusual signatures tightens. What we lack in direct answers, we gain in a map of where to look next. For those considering long futures, technosignatures may be the only safe answer to the paradox. Where broadcasting carries the risk of alerting unknown neighbors, searching silently introduces no extra danger. The data come to us without sending anything back. This asymmetry makes it one of the few ways to balance curiosity with caution. To put it simply, technosignatures allow us to gather evidence, even in a galaxy where everyone else stays quiet. Yet the implications circle back to us. If these methods eventually succeed, the discovery will not come from one clear signal, but from subtle, indirect fingerprints. And if no footprints appear, even after decades, we may confront a deeper conclusion about solitude. That tension fuels debate not only about how to search, but about what role humanity itself should play. If silence persists, should we remain observers, or should we take the risk of speaking first? Should we stay silent? The issue is no longer theoretical. Humanity is approaching a real choice about how we present ourselves to the galaxy. The question is straightforward but unresolved. Should we actively broadcast our presence, or should we remain silent? Unintentional radio leakage from television towers and broadcast stations has already diminished with modern telecommunications, but deliberate, targeted transmissions remain possible. The decision is open to us, and the consequences are hard to predict. Our past gestures reveal that the urge to reach outward has long existed. In 1974, the Arecibo telescope transmitted a tightly focused digital signal toward the globular cluster M13, packing basic information about human biology, numbers, and technology into a sequence of bits. 3 years later, the Voyager spacecraft launched with golden records, engraved discs carrying sounds, music, greetings, and images of our planet. These efforts were symbolic, unlikely ever to reach listeners, but they drew a clear line. Humanity has at times chosen not just to listen but to speak. With today's more powerful instruments, repeating such gestures on a much larger scale is technically possible, and the debate over whether we should attempt it has grown sharper. The arguments divide into two recognized positions. The first is proactive messaging. From this perspective, sending deliberate signals is a natural extension of exploration. Supporters argue that silence ensures a deadlock if everyone waits for others to speak. First, no exchange will ever take place. Advocates point to the Arecibo message and the Voyager records as precedents that expressed a basic human drive to connect and to represent ourselves in the cosmos. With better targeting of promising nearby stars, they believe clear signals could at least place us on the map. Even if the nearest reply came thousands of years later, they argue the risk is outweighed by the potential legacy. The second position is caution, sometimes called the no-contact approach. Here, the reasoning draws from both practical warnings and darker thought experiments. Stephen Hawking repeatedly cautioned against announcing ourselves, comparing such actions to early human encounters where technologically uneven contact often ended in exploitation. The dark forest hypothesis adds further weight, proposing that silence among civilizations could reflect a rational survival strategy. Those who announce themselves expose their location to unknown predators. Within this framework, deliberate broadcasting is not harmless curiosity, but an irreversible gamble. Silence may not guarantee safety, but exposure removes the option entirely. Much of the tension lies in our shifting detectability. For most of the 20th century, Earth's technology leaked powerful, unfocused signals. By now, with the transition to fiber optics and more efficient digital networks, that leakage has sharply reduced. Our planet may already be growing harder to detect by accident. Remaining hidden in the future may require no major effort. Simply continuing current trends could make Earth quieter on its own. That creates a narrow decision point. Deliberate messages will matter more than they ever did in the past, because they would stand out starkly against our fading background noise. The choice is therefore sharpened. Proponents of active signals argue that we control the message better if we send it intentionally, rather than waiting for distant observers to interpret accidental emissions. In their view, it is better to define who we are and what we value than to allow random fragments of our technology to stand as the only testimony. They describe it as a question of agency. Hiding may be impossible forever, so it is wiser to shape what others learn about us. Opponents counter with the scale of risk. They note that the probability of harm may be low, but the consequences incalculably severe. A single detection by a hostile or indifferent machine-based intelligence could alter Earth permanently, and once a message is sent it cannot be retrieved. They add that premature contact could short-circuit our own development, leaving us dependent on frameworks we barely understand. To them, patience is not cowardice but prudence in a galaxy that shows no signs of welcoming conversation. Both sides agree on one point. The decision has long-term consequences that extend far beyond our own lifetimes. Even a small campaign of broadcast toward nearby star systems would define Earth's visibility for centuries to come. Silence, in contrast, would preserve ambiguity. Future generations could reassess with better knowledge and stronger tools. There is no undoing a transmission once it has left the Earth. The heart of the debate comes down to whether we prioritize curiosity or survival. The temptation to seek connection runs deep, expressed in rituals of exploration across cultures and centuries. At the same time, the lessons of history and the warnings of theoretical scenarios weigh just as heavily. A galaxy that appears ordered by silence may already embody an unspoken rule. If so, speaking out is not a neutral step, but a challenge to a survival pattern we do not yet understand. For audiences today, the question is immediate. Should we risk making ourselves visible to unknown others, or should we discipline ourselves to remain quiet and watch? If you were on the decision board, would you broadcast? Why? This is not just a technical puzzle. It is a profound ethical dilemma about how a singular planet should represent itself after billions of years of uninterrupted evolution. The debate remains unresolved, but the stakes grow clearer with each discovery. As we learn that planets are common and habitable conditions may be widespread, silence takes on sharper meaning. The decision is no longer about whether the cosmos contains others. It is about how humanity chooses to step forward in a place where no other voices come back. The quiet sky demands interpretation, and what we decide to do next may decide whether Earth's story continues safely or risks exposure. And just as these arguments sharpen, the broader situation around us shifts as well. The latest discoveries show that planets are abundant, yet the signals we expected have not appeared. The evidence forces us to face the pattern directly. Something about survival or behavior may be silencing the rest. For humanity, that realization lands at a critical moment, shaping 2025 as a turning point. The numbers are in, and they leave little comfort. The 2025 warning. The warning that emerges in 2025 comes from a convergence of evidence, not from speculation. Three realities now stand side by side. The data show that planets are common, the silence grows deeper as our tools improve, and the pattern points to dangers that mirror our own path forward. Together they form what researchers increasingly describe as the 2025 warning, a reminder that the silence itself may be the most important signal we have ever received. First, the numbers. By mid-2024, NASA's Exoplanet Archive confirmed more than 5,600 planets, with the official announcement set to tip over 6,000 sometime in 2025. This number represents just a fraction of what is truly out there, but enough to shift the old question of rarity. Planets are no longer exotic discoveries. They are a feature of nearly every star system. Many of these worlds fall into the orbital bands that allow for liquid water, and observations from the James Webb Space Telescope are beginning to probe their atmospheres in detail. The implication is unavoidable. Habitable real estate in the galaxy is not thinly scattered but widespread. That means conditions like Earth's, at least on the surface, are neither unique nor improbable. Against this backdrop sits the paradox. If worlds are abundant and technology like ours is possible, the galaxy should not appear still and empty. Yet it does. Projects like Breakthrough Listen, which in 2023 carried out delicate occultation-style monitoring of 27 exoplanets, continue to return null results. No narrowband beacons, no clear technosignatures. JWST has added detail on atmospheres, waste heat searches look for infrared excess, and radio observatories cover billions of narrow channels. Across all these methods, silence persists. That is what the paradox now reduces to in plain terms. Abundance is confirmed, contact is absent. Faced with that contradiction, two explanations dominate current debate. The first is collapse. Civilizations may reach technology but fail to sustain themselves, undone by environmental stress or runaway systems they cannot control. The second is concealment. Civilizations may survive, possibly even thrive, but adopt silence as their strategy, avoiding risk in a galaxy where exposure could attract threat. In both cases, the silence is telling us something. It is the echo of collapse, or the footprint of caution, repeated across the stars. This framing matters because both possibilities line up uncomfortably with our own situation. On one side, the climate crisis shows how fragile biospheres may become once large-scale industry accelerates. We are watching ice sheets destabilize, biodiversity collapse, and carbon accumulate on a scale measured in centuries, not millennia. If similar dynamics unfold elsewhere, then many civilizations may have reached our level only to unravel quickly thereafter. To a distant observer, that process would resemble what we see now: atmospheres shifting, then silence. On the other side, artificial intelligence is advancing at a pace that forces new questions. Machine systems already influence economies, decision-making, and research itself. Some researchers frame AI as a potential great filter. Either it extends a society's reach indefinitely by creating durable, post-biological successors, or it removes the biological phase entirely, leaving no interest in communication. Both forecast a kind of silence. One is terminal, the other is deliberate. As these factors sharpen, the warning takes shape. The galaxy is not empty. It is littered with the outcomes of civilizations pulled down by their own limits or rendered invisible by their successors. For us, the question is whether to interpret this absence as chance or as pattern. It is easier to assume the universe is quiet simply because contact is difficult, but the numbers now argue against dismissing the problem. Abundance plus silence equals a lesson. The conditions are everywhere, but enduring voices are not. This is why scientists and writers alike describe 2025 as a hinge moment. The paradox no longer floats as an abstract equation. It reads as something closer to advice. The silence does not guarantee doom. It tells us what survival requires. It suggests resilience is not optional, that civilizations flicker unless they achieve balance. The warning is not a sentence but data pointing to priorities. If worlds like ours tip into climate instability quickly, then stability must be our focus. If machine intelligence tends to drift into indifference or dominance, then alignment and control matter from the beginning. Survival is possible, but only if choices are made with the filter in mind. There is also an alignment of timing. Humanity makes these discoveries just as our own crises peak. Climate records break each year. AI moves from labs into global infrastructures. Economies run into planetary boundaries of energy and consumption. The road ahead looks deeply like the branching paths that silence may already have taken on other worlds. That timing is its own kind of message. The absence of signals intensifies at the precise moment we most need to hear them. Interpreted cautiously, this coincidence does not argue for despair but for urgency. The message of the 2025 warning can be expressed clearly. Do not confuse silence with safety. Null results are not a reassurance that the galaxy is empty. They are reminders that survival is conditional, fragile, contingent on behavior. Every missing signal may represent a society that stumbled where we now stand. Seeing those gaps across thousands of stars is like glimpsing the mirror of our potential trajectories. It is an invitation to consider not only whether others exist, but why they disappear. One way to reframe it is simple. Silence functions as the galaxy's baseline, the most consistent result we have. That steadiness is itself a pattern. The normal outcome of reaching intelligence appears not to be long-term visibility. That should not make us fatalistic. Instead, it clarifies that being visible, being long-lived, detectable, and sustainable is the exception. To join that minority, restraint matters as much as curiosity. Stability counts more than reckless expansion. The silence shows what paths fail. It says less about whether endurance is impossible. This is why some describe the paradox not as a discouragement, but as instruction. The data show us planetary systems are everywhere. The silence shows us why they may not last long. Balancing those two facts provides a map. The galaxy may be rich with opportunities, but fragile in outcomes. The warning is to choose survival as strategy, not as afterthought. In practical terms, that means linking cosmic lessons back to Earth. Climate mitigation, resource management, careful deployment of advanced AI. These are not just local issues. They may be the exact crossroads where civilizations succeed or vanish. If silence marks repeated failure, then responding with foresight is how we exit the pattern. The reason to care about exoplanet counts and radio sweeps is not curiosity alone, but recognition that they spotlight the stakes of our own future. The 2025 warning, then, carries three pieces of clarity. The data show abundance. The paradox restates silence versus expectation. And the explanations, collapse or concealment, mirror the very pressures now tightening on our world. Taken together, they offer direction. We cannot treat the void as reassurance. We can treat it as guide. So if the silence is a warning, what concrete steps follow? That's the final payoff, what we should do next. The conclusion is that silence itself carries instructions. From the evidence, three implications for humanity stand out. First, planetary stability is not optional. Studies on runaway greenhouse states show how quickly habitable conditions can vanish without restraint. Second, the safer course is to refine our techno-signature searches using tools like JWST and Breakthrough Listen, rather than broadcasting into the dark without knowing who might hear. Third, artificial intelligence must be treated as an existential variable, since it could either extend our survival or end it outright. Which of these concerns strikes you as most urgent? Share your thoughts in the comments, and subscribe if you want more analysis of how cosmic silence shapes human choices. Where we look in the sky should also change how we act on Earth.